We have an example question for equilibrium, a horizontal bar. So a 1.6 meter long, 12 kilogram uniform bar is hinged on the left end and pulled at 1 meter from its left end by a cable. So let's see, here's a hinge. So I'll place this here. And this bar is pulled 1 meter from the left end by this cable, and the cable has a 30-degree angle. The whole bar's length is 1.6 meters, but there's also a 4.8 kilogram load is suspended below the bar at 1.2 meters. So this distance is 1.2 meters, and the total length of the bar is 1.8 meters. This is 4.8 kilograms, 4.8, and the bar is 12 and uniform. So the questions that are not really written here, the questions are asking about the force from the hinge, the horizontal component, the vertical component, and also the tension from the cable. So this is a relatively complicated problem with equilibrium. So we need to analyze first. What we need to analyze is to analyze bar. Analyze the bar. So the bar needs to be in translational and rotational equilibrium. And in order to analyze rotational equilibrium, we need to have an axis of rotation. So where do we make the choice? So an axis of rotation. So we'll just pick the hinge. This is a typical choice, although it may not be the best mathematically. We'll just pick that. So axis of rotation is hinge. All right, and then we can calculate the lever arms. So I'll draw the forces out first on the diagram, and then we'll look at lever arms. So just change the color. The hinge here actually supports the beam. It pushes the beam towards the right. Just imagine if this is a wall. If this wall section has a hole and nothing is pushing or supporting to the right, this bar will just slide into the hole. So there must be some support to the right by the hinge. And there's also an upward lift from the hinge. You can imagine that without that lift, the bar's left end will slide down. So we'll call this a force vertical, the hinge vertical, and we'll call this force horizontal. Okay, and besides this, let's see, 1.8 meters. Now we have roughly here, this is the center. So around center of mass, there's also gravity. And over here, there's a force pulling down from the load. Let's call this force load. And then over here, there's another force, which is tension. So this is tension. So it's rather complicated. Alright, so let's return to our choice, the axis of rotation being the hinge. With this choice, the lever arms, several lever arms are zero. For example, lever arm of the horizontal hinge force. This horizontal hinge force goes through the hinge, so there's no distance. Lever arm of the vertical hinge force is also zero because this force also goes through it. And then we have some other non-zero lever arms, such as lever arm of gravity. It is halfway across the whole bar of 1.6 meters, so it's 0.8 meters. And then lever arm of the load, it is 1.2 meters away from the left end, so it's 1.2 meters from the hinge. And then there's also this lever arm of tension. It's not that easy to find, but we can draw a line. Let's use a different color for lever arm. So the lever arm here is from hinge perpendicular to the line where tension has line of action. So this will be that. I'll extend tension. This is tension's line of action. Alright, so this is our choice of lever arm tension. Back to black. So if you look at this lever arm tension, this right angle triangle here, 90 degrees. This right angle triangle has a hypotenuse. This is where the cable is attached to is 1 meter. So the hypotenuse is 1 meter, and this is opposite to the 30-degree angle. So this is actually the lever arm is 1 meter times sine 30 degrees. So it's 0.5 meters. Okay, so now we have all the lever arms. We can also look at the signs of each torque. So let's determine the signs of each torque, starting with the gravity's torque. So with gravity acting alone, it'll tend to rotate the bars right and down. So this traces a clockwise rotation. So gravity has a negative torque because clockwise. Right? So torque gravity is negative. And then torque of the load does the same thing, rotates the right end of the bar down. That traces a clockwise rotation, less than 0. Then torque from tension must be greater than 0 because you can't have all of those less than 0 and still balanced because tension tends to pull it up, right? So that traces a counterclockwise rotation. Okay, so let's put the equilibrium together in rotation. So net torque is gravity's torque, so is minus mg times lg, then minus m of a load, g times m L of the load, then plus force tension, let's write that, tension times L tension, and that is equal to 0. So we can plug in the numbers and see what happens here. Minus, this is the uniform bar, so 12 kilograms times 9.8 times lever arms 0.8 minus mass of load 4.8 times gravity times lever arm plus tension times lever arm equals 0. So apparently we can solve tension out. So we can solve tension, and tension is 301 newtons after plugging these into a calculator. Okay, so now we have tension. We still don't have the any knowledge of the horizontal or vertical hinge force because they were not present in the rotational equilibrium. So we need to do translational equilibrium in order to find them. So for translational equilibrium, we need a free body diagram. So let's draw the free body diagram below this diagram. So we have x-axis and we also have y-axis. We have gravity pointing down. So let's change color. So we have gravity pointing down, hinge horizontal force to the right, hinge vertical force up. We also have tension at 30-degree angle. Tension can be decomposed into tension horizontal and the tension vertical, Tx and Ty. So now we have a complete picture of the force diagram, 30-degree angle. Back to black. Now we can do force net x equals 0. So this gives you horizontal hinge force minus tension x equals 0. And that is horizontal force minus tension x is tension times cosine angle equals 0. So we can solve. We can get force horizontal is equal to tension 301 times cosine 30 degrees. So with a calculator, you can find tension horizontal, which is 261. So 261 newtons. And then from the net force Y equals 0, we have vertical hinge force plus tension Y component minus gravity equals 0. So now the vertical hinge force is equal to gravity mg minus tension Y is tension sine angle. So we have tension vertical force from hinge. This mass is, I think I missed one mass here, but I can do this. I can just say that this is Fg plus this Fl, the load. I think I missed it. Okay, so G plus L, we'll just add them together. This is going to be the total mass. So we'll have 12 kilograms plus 4.8 kilograms times G. 9.8 minus 301 sine 30 degrees. And this should give us 14.3 newtons. Okay, so since we still have some space, we can do some more. We were picking our axis rotation at the hinge. What if we picked it at a different location? Will that change something? And that will not change the free body diagrams and the force analysis, but it does change the torques. So let's draw a line here. And over here, we'll pick axis of rotation at a different spot. So which spot can I pick? Alternative axis rotation. So we had it over here. So let's call this AOR right here. And we'll pick another spot right here where the cable is attached to. So right here, this axis of rotation. I can probably change to a blue color to indicate this lever arm corresponds to that axis rotation. And I'll just also color code that. Now we have this. This is where the cable is attached. Okay, so the advantage over here is once the axis rotations here, this tension here will have no lever arm, so it makes it easier. We don't have to use any trigonometry if we don't want to. But what it makes it slightly more difficult is to figure out the distance between the axis rotation and these other places. For example, the load here has this lever arm of load. So 1 meter to 1.2 meter. So this load lever arm of the load is 0.2 meters. And the lever arm to the gravity here, this is lever arm gravity, is this is 0.9 meters. Let's see. Sorry, not 0.9 meters. 0.8 meters. And here's 1 meter, so this lever arm is 0.2 also. So lever arm G 0.2. That should be 1.6. All right. So back to calculating lever arms. The horizontal hinge force has 0 lever arm because that still goes through the axis rotation. The vertical hinge force has this lever arm. Okay, so that's a whole meter. So this is 1 meter. And we need to redo the torque because now torque tends to do different things. For example, tension has no torque. Now the load will tend to rotate the right side down to make it into this clockwise rotation. So torque of the load is negative. On the other hand, now the gravity is on the left side of the axis rotation will tend to rotate this bar down. Let's imagine that this hinge is gone. No other forces, hinge forces are all gone. We're just imagining this one gravity rotating the object. The only thing that we refer to is this axis rotation stays in place. So gravity pulls the left side down. That makes it a counterclockwise rotation. So gravity has a positive torque. And then the vertical force here has an effect of rotating clockwise. So the vertical force has a negative torque. This is vertical. Okay, so now we have all these. We can put them all together. Net torque equals negative m of a load G and times this L of load positive m G L of G and negative this is vertical force times L vertical equals 0. And here we have this as unknown. Instead of tension, vertical force now is an unknown. So vertical force is equal to minus m load G L plus mg lg then divided by lever arm of the vertical force. So now we can calculate the vertical force out, and this is the same as before. But interesting enough, by picking different axis rotation, we can find out different unknown forces first. So now we know the vertical force will still do the same exact free body diagram analysis, except that the vertical force is known. So in here, this equation we can solve for tension, and then we can go back to this first equation to solve again for horizontal force. So the steps are slightly different. What you can even do is you can pick axis of rotation, the blue choice, and you solve for one force, you solve for tension, and then you pick your axis rotation to be the green choice, a second axis rotation, and then you get another force out, and then all you have to do is just solve one of the two free body diagram equations. Although that's not really my choice, because sometimes it could confuse people how many equations you need. This is at times it's easy because this way provides you one force out of one axis rotation situation with a rotational equilibrium. Maybe that is the only force you're expected to solve, and that saves you time. Thank you.